Okay, let's start with the big one. What if everything we think we know about reality, I mean the really basic stuff, even complex physics, what if it's all built on a kind of foundational error? Like, imagine our most precise scientific rules, the ones we think govern everything, actually came from a basic misunderstanding of how we even get knowledge in the first place.
That's a pretty radical starting point.
It is, and that's really the core of our deep dive today. We've got this fascinating set of sources that propose a completely new way of looking at reality, at knowledge, maybe even physics itself. And this isn't just, armchair philosophy. The idea is to give you, the listener, a kind of shortcut to understanding what could be a major paradigm shift in science and thought.
Yeah, it promises some genuinely surprising insights.
Totally. Like how some really famous paradoxes, in math and physics, things that seem impossible to solve, might actually just devolve with a simple shift in how we look at them. So let's get into it. The sources kick off with this central idea, almost like a rule. First, acknowledge limitations, only then make distinctions. Now, that sounds kind of simple, maybe obvious, but the argument is that this is where we usually go wrong. We make distinctions first, without really checking if we can always make them precisely, without exception.
Exactly. It's what the sources call the classical error, like trying to draw a perfectly straight line on a bumpy surface and then acting surprised when your measurements based on that line are off.
Ah, okay. And this error has consequences.
Oh, absolutely. Huge ones. Look at Gödel's incompleteness theorems. I mean, that shook mathematics, right? Showing that any formal system complex enough for arithmetic has true statements you just can't prove inside the system. It's fundamentally limited.
The system itself has boundaries.
Precisely. Or Russell's paradox. You try to define the set of all sets that don't contain themselves, and bam, you hit a logical wall. You can't just define anything you want without checking if the definition itself creates a contradiction.
Okay, so math and logic.
Yeah.
What about physics?
Well, quantum mechanics is a perfect example. We want to know exactly where a particle is and exactly how fast it's going. But the theory and experiments tell us the very act of measuring one affects the other. There's this inherent, inescapable uncertainty or noise.
A limit to precision.
A fundamental limit. And even something seemingly simple like the number pi. In numerical math, we always use approximations, right? Because a truly exact finite description just isn't possible in our standard number system. Our tools, our descriptions, they have built-in limits when they meet certain realities.
So it sounds like these aren't just quirky problems. They're signals that we're bumping up against the edges of our descriptive systems because we didn't acknowledge those edges up front.
That's the core argument.
Yeah.
And the benefit of flipping the script, of starting by saying, okay, here are the limits, is potentially huge. Well, for starters, you might just avoid creating paradoxes in the first place. You build the limitations into the system's foundation. It makes your reasoning more flexible, more robust, especially when dealing with really complex stuff. You don't get stuck in those logical cul-de-sacs.
Okay, so contrast that with how we usually think, say, in math or logic.
Right. So traditionally, we sort of define numbers as if they have this perfect, maybe infinite description. The new approach says, hang on, let's start by recognizing some things are describable, maybe only approximately, and some maybe aren't, not fully.
And axiomatic systems.
We've often built them like they're the final word, totally conclusive. This new view says, no, every system has boundaries, we need to know them. And language. We often act like it perfectly mirrors reality.
But it's a model.
Exactly, a powerful model, incredibly useful, but always a model, with inherent limitations, never the thing itself.
So why is making this shift considered so crucial? What's the big danger in not doing it?
It's about avoiding, well, pretending we have more precision than is actually possible. It's about avoiding unconscious assumptions that our models are complete, that they capture everything.
Right.
When we ignore the limits, we basically set ourselves up for logical errors, for paradoxes.
Right.
So the kind of meta conclusion from these sources is pretty strong. They argue this approach isn't just like a neat idea. It's necessary for consistency, for robustness. Every formal system, every scientific model should almost have a disclaimer. Warning, this is a model. It has boundaries. Here's what it can probably do. Here's what it definitely can't. Now let's use it.
That feels, I don't know, more honest and maybe even more powerful in the long run. Okay, let's take this idea, this limits-first approach, and apply it somewhere really challenging. Quantum mechanics.
Ah, yes. The deep end.
Right. The sources pose this really provocative question.
Yeah.
Is reality itself fundamentally quantum mechanical? Or is quantum mechanics actually a result of how we humans make distinctions?
That is a massive question. And the standard view, certainly for a long time, has been, yeah, reality is quantum at its base.
Because the evidence is so strong.
Incredibly strong. Experimental evidence is overwhelming. The double slit experiment, entanglement, superposition, these aren't just theories, they happen. And the mathematics of quantum mechanics predicts these things with stunning accuracy. It really looks like we found the fundamental rule book.
But there's a but.
There's a but coming from these sources. The counterargument is subtle but powerful. It asks, what if reality is only knowable in the way we distinguish it? Meaning, when we impose our distinctions, like, is it a particle or is it a wave? Maybe that's what creates the paradox. Wave-particle duality might be a feature of our description, not the thing itself.
Oh.
And when we try to measure something precisely, quantum mechanics tells us the measurement changes the system. It collapses possibilities. What if that reflects a limit on our interaction?
So the weirdness might actually come from us, from our limited way of carving up reality.
That's the suggestion. It leads to this idea that maybe quantum mechanics doesn't describe ultimate reality, what is, but rather it describes the limits of what we can know and distinguish within reality. It's more about the boundary between us and the world, or maybe the fact that there isn't a sharp boundary.
That sounds a bit like Bohr's complementarity, maybe, or Q-ism.
Exactly. It resonates strongly with those interpretations. Bohr saying wave and particle are complementary aspects needed for a full description, but you can't see both perfectly at once. And cubism framing quantum states as essentially an observer's subjective degrees of belief based on interaction. It shifts the focus from what is to what can be known by an interacting observer.
Okay, so we have two big pictures for QM. One, nature just is quantum mechanical weirdness and all. That's the realistic view.
Right.
Two, quantum mechanics describes the limits of what we can know or say about nature, because we're participants making distinctions. The epistemic or participative view.
Yeah, those are the main camps.
But then the sources drop something even more fundamental, something that kind of pulls the rug out further. What if there aren't lots of separate things out there at all? What if, and this is a quote, there might be only one object with properties taking local form so that we can emerge.
Okay, yeah. This is where it gets really deep. The idea is provocative. It suggests that fundamentally there's just one underlying something, one object, one reality.
And everything we see, touch, measure
Are just local variations, local properties, or patterns within that single object. Like waves on an ocean. The waves aren't separate from the ocean. They are the ocean, locally configured in a certain way.
And crucially, we're not outside looking in.
No, that's key. Our bodies, our measuring instruments, we're also just parts of this one object. We're patterns within the ocean, too. So all observation, all knowledge comes from one part of the object interacting with or distinguishing another part.
You can't observe the whole ocean if you're a wave in it.
Precisely. You can only observe relative differences, other waves, currents, local things.
Okay, wow. So if we take this one object model seriously, what does it imply for science? How does it change things?
Well, first, it suggests physics is always about describing differences, relationships, interactions between parts. It can never be about describing the totality, the one object as a whole, from some impossible outside perspective.
That avoids the need for an observer separate from the observed.
Exactly. It elegantly dissolves that old philosophical problem of dualism. There's no fundamental split between mind and matter or observer and world. It's all one continuous system interacting with itself.
And our scientific theories, like QM.
They become models of local relationships within this one object. They describe how parts influence other parts, how patterns emerge and behave. They aren't necessarily descriptions of an external, independent reality out there, but descriptions of the relational dynamics within the whole.
Why is that shift in thinking so important?
Because it provides a potential reason for why science works the way it does. Science relies on making distinctions, well, that's because we're part of the object, and distinguishing local differences is all we can do. It explains why there seem to be fundamental limits to knowledge, because we can't get outside the system to see the whole picture.
And it explains why models like QM emerge, with their focus on relationships and probabilities.
Yes, because maybe that's the best way to describe interactions between local states when you can't know the global state. This connects to some big philosophical ideas, monism, the idea of one fundamental substance relationism, where things are defined by their relationships, and this idea of participatory realism, where observation is an active participation.
So let's contrast again. The old, maybe classical scientific picture. Worlds full of separate objects. Science discovers objective laws out there. Measuring is passive observation.
Right.
The proposed model. One object. We perceive its local properties differences. Science describes relationships between parts of that object. And measuring is active participation within the object.
That's a really good summary of the shift. And to formalize this, the sources outline a framework. It's called Et en Objectkader voor Wetenschap en Weten, basically. The one object framework for science and knowing.
Okay, what are the key points of this framework?
It lays out about 7 core ideas. First, the prime thesis. Reality is one object, we're part of it, simple but fundamental.
Got it.
Second, behavior is not law. This is interesting. Nature just is. It behaves according to its internal dynamics. What we call laws are our descriptions of observed patterns, not external rules nature follows.
Ah, okay, laws are descriptive, not prescriptive.
Exactly. Third, knowledge is relation. All knowing comes from making distinctions within the one object. Measuring, knowing these are interactions between parts of the same whole.
Consistent with what we just discussed.
Fourth, acknowledgement of limitations. We have to accept we can never describe the whole thing from the outside. We work with local relationships, approximations.
When it's built in again.
Fifth, models are tools, not reality. Maths, language, scientific theories, incredibly useful tools, but they are tools distinct from the reality they try to describe.
Right. The map is not the territory.
Precisely. Sixth, reality is continuous and relational. No absolute fundamental separations. Particles, fields, space, time, observer, they're all relative manifestations, interconnected forms within the one object.
No hard lines.
And seventh, observing is participating. Every measurement fundamentally involves using one local difference, say in our instrument, to register or interact with another local difference in the system being measured. It's an interaction within the one object.
Okay, that's a really coherent picture. What are the claimed advantages of thinking this way?
Well, the big ones are potentially preventing paradoxes by acknowledging limits up front, allowing for a rigorous science that isn't absolutist, claiming final truth, but also isn't just anything goes relativism, and maybe the most exciting, offering a path to reconcile quantum mechanics and classical physics, seeing them not as contradictory, but as different kinds of approximations, different ways of describing relationships within the same underlying reality, perhaps at different scales or under different conditions.
So it's not QM or classical. It's potentially both, as limited models of one thing.
That's the hope.
Now, okay, this one object framework is conceptually really powerful.
Yeah.
But you can see how someone might say, okay, that's great philosophy, but how do I actually use this? How does it connect to the physics I do in the lab? It can feel a bit abstract.
Absolutely. And that's a fair criticism of many philosophical frameworks. They can seem disconnected from practical application.
Which is where the next part of our sources comes in, this DENK model from destekel.nl.
Exactly. Destekel's thought model is presented as an explicit attempt to bridge that gap. It aims to take the core ideas of the one-object framework and build something concrete, something that connects directly to, well, actual physics and mathematics as we know them, moving from the why to the how.
Okay, so how does this model try to make the abstract framework more, well, usable?
Yeah.
What are its advantages?
The sources highlight a few key things. First, practical applicability. It's designed to link up with actual calculation methods used in physics. Second, testability. It aims to generate models that make predictions comparable to current physics, so you can actually test them against experimental data.
So it's not just navel-gazing.
Right. Third, it tries to avoid dogma. It's presented as a research direction, something dynamic and open to revision, not a final fixed answer. Fourth, communication. By using mathematical and physical language, it aims to be more understandable and engaging for working scientists.
Makes sense.
And finally, it tries to prevent stagnation. It doesn't just stop at the concept. It suggests concrete next steps, research projects, simulation plans. It's meant to be an active program.
An engine for new research, basically.
That seems to be the goal. And one of the first really specific and quite tricky problems this destekel model tackles is fermions. How do you get particles like electrons with their weird properties to emerge naturally from this idea of a single underlying object.
Yeah, you mentioned fermions earlier. What's the standard problem again? Why are they so difficult to fit into a simple picture of space?
Okay, so fermions, electrons, quarks, the building blocks of matter, have these intrinsic quantum properties. The most famous is spin 12. It's not like a tiny spinning top. It's weirder. You rotate it 360 degrees, and it's different. You have to go around twice, 720 degrees, to get it back to the identical state.
Which is just bizarre.
It is. Plus, they obey the Pauli exclusion principle. Two identical fermions can't be in the exact same state at the same time. That's why matter takes up space. Now, standard physics usually says that to get these properties, especially the spin 12 thing, space-time itself needs a special kind of mathematical structure, a spin structure, that basic smooth Euclidean space doesn't automatically have.
So normal space isn't twisty enough for electrons.
Kind of, yeah. Usually have to add this extra structure by hand. It feels a bit tacked on.
Okay, so how does destekel's model, based on this one object being like an elastic medium, try to solve this? How does it generate spin without just assuming it?
This is where it gets really clever, proposing a kind of two-layer structure within the elastic medium itself.
2 layers.
Yeah, conceptually, the first layer is about stability. The idea is that the medium naturally settles into a stable, sort of almost spherical shape. Think of it like a perfectly formed, self-sustaining bubble or sphere within the medium. The sphere isn't perfectly smooth, maybe tiny bumps and dips, but it's incredibly stable because it represents a state of minimal internal tension or stress in the medium. Locally, it looks pretty much like our familiar Euclidean space, but globally it has this specific, stable, spherical form.
And how does this stable sphere form? What makes it stable?
Well, the research described uses combinations of mathematical functions called Legendre polynomials. These are functions that naturally describe stable shapes and vibration patterns on a sphere. Think of the natural ways a perfectly spherical bell would ring.
Okay.
By combining just a couple of simple Legendre polynomials.
So the medium itself wants to form this stable, slightly structured sphere because it minimizes internal stress. That's the first layer. What's the second?
The second layer is about dynamics on this stable sphere. It introduces what they call a band trick mechanism, essentially resonant patterns, like specific ways the sphere can vibrate or have circulating flows within it, emerge on this stable structure.
Like vibrations on the bell?
Sort of, but maybe more complex. And these specific resonant patterns, these dynamic movements within the spherical structure, are proposed to be the physical origin of spin 12. The idea is that traversing a closed path within this dynamic pattern inherently involves a kind of twist or phase shift analogous to the 720-degree rotation needed for fermions. It's like the spin property is generated by the motion within the stable structure.
Whoa, okay, let me see if I get this. Instead of needing space itself to have some built-in twistiness for spin, this model says the underlying medium forms a stable sphere, and then specific dynamic patterns within that sphere naturally behave in that twisty spin 12 way.
That's the core idea. It's generating the fermionic behavior dynamically from the medium's properties and stable structures rather than assuming it axiomatically. It gives spin a potential physical origin as a resonance in an elastic structure.
That feels much less arbitrary than just adding spin structure to spacetime.
It does feel more emergent, and this band trick idea connects conceptually to some deep math and physics, the relationship between rotation groups called SU2 and SO3, which mathematically underlies spin. Destekel's model tries to provide a physical, mechanical basis for why that mathematical structure, spinors, is relevant.
And does this connect to quantum field theory, too? QFT is our current best description of particles and forces.
Yes, that's part of the proposal. These resonances, these patterns within the sphere, could potentially be modeled as the basis for quantum wave functions or field excitations. The elastic medium itself provides the substrate for fields. The tension energy in the medium acts like the Hamiltonian, the energy operator in quantum mechanics. If you then quantize these resonant modes, well, the hope is you naturally get something that looks like a fermionic quantum field theory, where spin 12 pops out automatically from the symmetries of these resonant patterns.
So it's aiming for a unified picture, where the medium, its stable structures, and its dynamic resonances give rise to fields, particles, and their quantum properties like spin.
That's the ambitious goal. Of course, there are big challenges.
Like proving it rigorously.
Exactly. Showing mathematically and through simulations that these dynamics precisely reproduce all the known properties of spin 12 particles and their interactions, connecting it formally to things like Clifford algebras, which are central to the mathematics of spin. It's a huge undertaking.
But still, what an incredible conceptual arc. We went from questioning the very basis of how we make distinctions
Acknowledging limitations first,
to proposing this radical one-object reality,
where everything is interconnected parts.
and then seeing how that philosophical shift could inspire a concrete physical model, aiming to explain something as fundamental and weird as electron spin from the dynamics of an underlying elastic medium. It really drives home that aha moment. Maybe reality isn't just out there waiting to be passively observed, but is deeply shaped by how we, as parts of it, interact and distinguish.
Absolutely. And it leaves you pondering, doesn't it? If the universe is fundamentally this single dynamic entity, and particles and forces are just emergent patterns like eddies in a stream, what does that really imply? For consciousness, maybe. For finding a truly unified theory that connects everything, it certainly reframes the questions.
It really does. A lot to think about. We hope this deep dive has given you, our listener, some new ways to consider the very fabric of reality and our place within it. Perhaps it sparked some questions about your own assumptions. Thanks for joining us on this exploration.